Okay, folks, so in this lesson, we are going to study some properties of integrals. So these are facts that we know about how integrals behave that we can use to solve problems involving integrals. And they're useful to us because we don't actually need to know always what the value of the integral is in order to apply them. So I'm going to start by just solving this one. You already know how to do this from your previous lessons. But we're going to use this as kind of a jumping off point so you can understand why some of the properties work the way they work. Okay. So, like I said, you already know how to do that. So I anti-differentiated, right? And then I substituted in my bounds, subtracting the upper bound from the lower bound. Okay? Now, the first property is essentially this. It says the integral, let's say I have from a to b of f of x. Let's say I flip those two numbers around. That just negates the integral. Okay? So in this particular integral, if I put the 1 on top and the 3 on the bottom, all that would do would be to change the sign of my answer. Okay? And it's easy to see why that is, because what that would look like if I did that, if I reverse these, so it would just reverse these, right? So I'd end up with 5 minus 9, which would be negative 4. So that's the first property. So make sure you capture this in your notes. I'll leave it up to you whether you want to capture this example or not. But this is fact number 1. Definitely you need it for reference in your notes. For our next fact, so notice this is the same integral that we started with. For our next fact, I want us to think about this graphically. Remember that was equal to 4. So remember what this is saying, right, is if I draw my function, so this would just be a linear function decreasing with a y-intercept of 6, right? So if I draw that, what this is saying is if I highlight the area from 1 to 3, the area under that curve is equal to 4, okay? The way I got that, right, is I took the whole area of the whole triangle, right, and the area of the whole triangle was 9, and then I subtracted this area right here that I'm going to highlight in purple, which was 5, to get 4, right? So that's what we're doing graphically, and you probably have a decent understanding of that based on our work together previously. So what we're actually doing when we take an integral like this is we're taking our yellow area and we're subtracting our purple area to get the area that we want, which I colored in navy, right? So taking this whole triangle minus this little piece that we don't want to count because it's smaller than 1, gives me the area that I'm interested in. This also means that adjacent integrals are kind of additive, and I'll show you exactly what I mean. So if I wanted to know the integral of my function from 0 to 3, then obviously I could just calculate this, but I could also say that this is equal to the integral of the function from 0 to 1. So my first little piece, my purple piece, plus the integral from 1 to 3. Okay, so I can split these up or add them together based on the bounds, right? I can actually draw, so this would be a whole number line from 0 to 3, right? And this would be from 0 to 1, and then from 1 to 3. Okay, so we're doing the same thing, but I can divide this up into whatever pieces I want. Whatever pieces are convenient to me, essentially. So the second rule, the way you would write this down, is the following. Okay, so this is essentially just a more general version of what we saw up here. So this says that if two integrals are next to each other, I can add them up to find the area, the total area, essentially. And this helps us in actually a number of different ways, which we'll see when we tackle some problems here in a second. Okay, the last of our properties is a very simple one that is very intuitive. So let's say I take my original integral that we started with, I put 5 right here. Well, the result would be what you'd expect is I'd multiply times 5 on the right-hand side and get 20. Okay, so the way I can write this, then this is a convenient way to do it often when you're solving these, is I can actually write the 5 in front of the integral. So that kind of saves me a little bit of work because I can just multiply my result by 5 at the end rather than kind of carrying this 5 throughout all of my algebra. Okay, so here's how we'd write down this last rule. This is what you should capture in your notes. Okay, so this just says that we can, if we have this constant c, we can factor it out of our integral, just like we've always been doing since Algebra 1. Let's look at a couple of example problems about how these might look. Okay, so here is a Delta Math example, so you can take a second to read it. It says that f is a continuous function. The integral from -3 to 3 of f is 5, and the integral from -6 to 3 of f is negative. And then it asks us for this integral here. So I'll admit that this is a little bit intimidating. But you should notice something about the boundaries that allows us to use those adjacent integrals. Okay. So what we want to say is we want to find the biggest integral, and we want to say that the two smaller integrals are going to add up to the bigger integral. And we're not going to worry about this -2 just yet. So we're going to say, notice the biggest one is from -6 to 3, right? So we're going to say the integral from -6 to 3 equals, well, that should equal the integral from -6 to -3, so we're going left to right here, of f of x, plus the integral from -3 to 3. Okay. So pause, make sure you understand how I got that, right? I'm just saying, it's sort of like a number line. My first integral is from -6 all the way to 3. And then my other two integrals are from -6 to -3. And then from -3 to 3. Okay, so that's what I'm saying here. I'm saying that these two must add up to the whole line. And then I just substitute. So I know, and be careful here, I know that this left-hand side is equal to -2. And then -6 to -3, I don't know. That's what I'm trying to find, right? So I'm going to leave that alone. But -3 to 3, I know, is +5. And you should see where this is going now, right? So I plugged in what is given to me, and now I can do a little bit of algebra here. I'm going to subtract 5 on both sides. Okay. We're almost done. Drop my negative here. So what I do now is I can substitute, and then notice this constant is an integral that I know how to find, right? So I'd say that the integral from -6 to -3 of f of x minus, what was it, 2? Well, that's going to be -7 minus 2x, -6, -3. And then I just substitute, so -7 minus Be careful with your signs here. So this becomes negative 7 minus positive 12 minus positive 6. So negative 7 minus 6 is negative 13. Okay. So all you're really doing is you're building an equation with the integrals and then substituting what is given. We'll look at one more. Make sure you have this captured in your notes before you move on, though. Make sure you understand all the steps. Okay, so here's another example. It's very similar. But as you read this one, notice that my bigger number, negative 2, is bigger than negative 3. So this integral is set up backwards. It's actually called an improper integral. It's set up backwards, right? So what I want is for my smaller number, my lesser number, to be the lower bound. Okay, so what I'm going to do is I'm going to rewrite this one. I'm going to flip those. I'm going to say this is now the integral from negative 3 to negative 2 of f. And because I've changed my bounds, I've reversed them, that changes the sign. And then that's going to help us solve the rest of these. So notice what I want is the value of negative 3 to 10 of f of x dx. And notice this 1/3 can come out too. So what I'll say, this is the biggest integral that I have. I'll say this. Okay, just like the last one. So I said the biggest integral is equal to the sum of the two smaller integrals. And notice rewriting this is convenient because then it goes in order. Negative 3, negative 2, negative 2, 10. And I'm just going to make my substitutions. So on the left is what I'm looking for this time. So this stays here. Then here I get positive 6 because this is this integral now. And then here I get plus 3. So 6 plus 3, this has to be equal to, well, that means, remember what we want is 1/3 of that, right? That's it. So that is properties of integrals. This is a great example of capturing your notes because this actually hits all three of the rules we discussed, right?